values happen at the same time. And then it moves on to another condition. So in this text description, it's like the loads varies a long time, but it has some kind of magic. It will switch to another condition at the same time, which usually is not the case in reality, right? So this is time, this is the load, some of the load, and this is condition number one, this is condition number two. If the fluctuation of the loads looks like this, of course it's easy to handle, and you can study the mean value and you can study the amplitude, so you know what to do later on. And also, these are like two extremes, and those two extremes represent two extreme conditions of the moment. Okay? So it's like inside the shaft at some position right here, 200 something, 200 something, 250 something. That would be somewhere here, right? Somewhere here. That's the location for worst bending, the largest bending moment. And since we are, the shaft would be, let's see what's the value for these. They are negative, I think. They are, yeah, the shearing force, yes, these are negative. So your shaft will be bended like this way. If I exaggerate the shape of the bending, and this is where that is being bended the most, and it's like it's being bended in this way, and in another like this is the level of bending, and in condition one, and the level of condition two being bended more. Do something like this. Okay. So if you study, let's say, a point on the top, that's where you have the largest tensile stress, normal stress outward. So it's gonna be like this from the top. So the stress right here is gonna be like this. If in reality, if the force is switching from mode 1 and mode 2 in that way, then the stress is switching like that. But of course, this doesn't happen in reality. In reality, it's gonna be like a curvy, right? This is your stress. So now you know, at this particular point, the stress is getting larger, smaller, larger, smaller, but it stays tensile. Okay? But this particular location is right at this area, like right at the corner. So yesterday we mentioned there could be effect of stress concentration. So that's just assume the location is right at the corner, and let's just use the table to figure out the stress concentration factor and study how much larger the stress is going to be due to the effect of stress concentration. So if we take a look at the bending part, um, the problem mentioned the radius at the corner is 2, and we will study the smaller diameter, not the bigger one. So the smaller part is 30. Is this 30? Yeah, right here. The diameter of the shaft is 30. So the thinner part is 30. Okay, so that gives us a value 0.07. That's why we will have a straight line at 0.07 for both cases. Why do we study two tables? Because we have bending and also twisting in this part. Now, the ratio between the big diameter and the small diameter is given by big D over small d. That is 35 over 30, so 1.17. And you don't have 1.17 over there in the curves. It doesn't show that exact number, so you kind of need to find it in between 1.2 and 1.1. So just pick up somewhere, and that's where you got your K. So your KT is 1.7 something, like 1.7. In my reading last time is 1.76. So this would be the stress concentration factor for static load and normal stress. And if you do the same thing on the right hand side, you will get KTS equals to around 1.45. That is static load but shearing stress. Okay? So we will be applying these two numbers into our design equation. This problem, okay, mentioned the shaft is not rotating, however, the belt tension fluctuates. So still, it's a dynamic problem. Since it's a dynamic problem, we also need to figure out the stress concentration factor in the fluctuation part. So we need to read these two tables, the Q and the QS. So right here, that table gives us the notch sensitivity, Q. The right-hand side gives us QS for the shearing. Okay. And we will be basically, I think we are just using, okay. Did the problem mention is steel? Maybe not. No, I forgot to mention this shaft is made of steel, but the strength of the material is close to within the range of steel. So let's just use steel, assuming the shaft is made of steel. Now, if you look at the notch radius, which is the radius of the rounding, which is 2, and the problem mentioned the ultimate tensile strength is 500 megapascal. So 500 would be somewhere between 0.4 gigapascal and 0.7 gigapascal. So it's like a level around here. Okay? And then you end up with a point. So this would be the level of 500 megapascal. So that gives you this point. So you get a Q value around 0.76 based on my reading. And then you do the same thing on the right hand side. You get the Q value around 0.8. And you will be using these two equations to get KF and KFS. Okay, just plug in KT and KTS. So you will be having KF and KFS. So KF would be the stress concentration factor for dynamic load and normal stress. Okay, the other one is dynamic and shear. So you have the four K values, four stress concentration factors for different load conditions. Now we can look at the design equations. So let's come here. So, if you use the Moore circle, and if you compute for the okay, there are two extreme conditions, and if you use the two extreme conditions to do Moore circle analysis separately, you should be able to get two different Moore circles. So one would be maybe somewhere here. The other one would be somewhere here. Okay? So that's one way to do it. You can do Moore circle analysis twice. And then you will be studying for the principal stresses in both conditions. So it's like you have a S1 condition 1 and S1 condition 2, right? And you will have a S2 condition 2 and S2 condition 1. With those, you then realize, okay, S1 time is fluctuating in a certain way, so you can have S1 average value and also S1 the range, right? The amplitude. So or you can say mean or amplitude, right? That's one way. What I'm having here is a different way. I can tell you, both approach gives different answers. So I think if you, because this is not, this approach right here is not doing Moore circle twice. This is by studying the fluctuation and then get the mean effect and the fluctuating effect, separate them, and apply to the Moore circle equation separately. So that's one approach, and the other approach right here is first separate the mean part and the amplitude part. And plug in design equations, and of course the same equation, the Moore circle equations, separately. So it's like you take the average, do the statistical analysis, and get mean and amplitude first, and then plug in equations. Over there is like you you don't take mean and amplitude first. You do it last. You do it the last. So I know the answer will be slightly different. For your exam, either way will be fine. So I know the answer may be slightly, the true answer will be slightly different if you use two different approaches. Okay? So in the exam, I may even solve for the solution. I will try to solve it in both ways and show them as a general answer. So your answer could be either one of them, but it won't be change. The variation won't be too much. When can these two approaches be exactly the same? If the design equation that we apply are linear, then the analysis should be the same because they are having linear relationship. However, as you can see right here, we have a square root, we have a square terms and square root terms, so it's not linear. But it won't vary the answer too much. Okay, so let's take a look at the approach that I have done in the slide. So earlier we had the moment diagram, and from here we found the two extremes. From the two extreme conditions we study for the mean moment and the amplitude moment. So that's what you have right here, the mean and the amplitude. Okay? And for the torque, the problem also mentioned the torque fluctuates. The torque will fluctuate, of course, because the belt tension varies. So it's like you're twisting this harder, but with a weaker torque, and a little bit harder, and then release a little bit, but still keeping the torque. So the level of the torque fluctuates between these two levels. So it's like you're solving for the torque separately, condition 1 and condition 2. And with these two different conditions, you have two extreme torques, and then you can get mean and amplitude. So in this particular case, even the shaft is not rotating, but the belt tension is fluctuating. So it's being twisted dynamically and also being bended dynamically. So here, when you plug in for the normal stress and the shearing stress, you plug in the same equation, but now you already use the mean value and the amplitude value to plug in. Okay, so it's like you have a mean amplitude, mean normal stress, amplitude normal stress, mean shearing stress, and the amplitude shearing stress. So you have those four values. Now you use those values to compute for the principal stresses. Then you directly just plug in. Okay, this is where I said you may have a variation with this approach. Okay, so just plug in. Okay, once you plug in for the mean part, just plug in the mean values. Amplitude part, plug in the amplitude values. So at the end, what does it mean? This approach shows that the first principal stress has a mean of 143 megapascal with plus and minus fluctuating 33.3 megapascal, something like that. Okay? Now, this is with stress concentration already. Where are the stress concentration factors? These pre-multipliers. Okay. So that's why I like to have a table of that one next to my solution sheet, so I know which one to plug in. Okay, so there are 4 different values, and you need to plug in at the right position. And then here are some values that was determined in the previous lectures where we didn't consider stress concentration. This is for you to compare. Right here you can see with stress concentration, the first principal stress is getting larger compared to without. And also the level of fluctuation is bigger. For the second principal stress is not changing too much because we had a problem that has pretty small compression. Okay, so all the matters the most is the first principal stress. Okay, now we need to plug into our design equation. So for the design equation, no matter which one you're using, you need to compute for the von Mises stress. And this is a plane stress problem, so we can use the von Mises stress equation on the top. And over here, they are already including the consideration of stress concentration effects. Because when you compute for the principal stresses, you already apply the K values. So now in this design equation, you are already considering stress concentration. Okay, so just plug in, and then you get some answers on the right. And use it for the design equations for fatigue. There are 4 different models, and those mean and amplitude values are going to be divided by different stress levels. Depends on which model you're using. So go back and review which one is which one. And at the end, you end up with 4 safety levels, 3 safety levels. And smallest one means you have you are very conservative. So you think your safety level is low. And if you have a large value, that means you are aggressive, right? So in this particular case, how come yield line is having a lower value? Okay, so we can take a look at the, this is the mean part, this is the amplitude part, this is the yield line, and here is Goodman, and here is your Soderberg, right? 3 different lines. You can kind of observe where is your design point. So your mean value of your von Mises stress is 143, and the amplitude part is 33. So it's the mean part is around 4 times larger than your amplitude part. So your design point, it will be somewhere here. Okay. So safety level is like the safety margin, the distance between your design point and that limit state. I didn't put numbers here, so maybe the point is not here, maybe somewhere on the right. So let's get the values more accurate. Maybe I make a drawing larger. So the yield strength is 250. Here is the amplitude. Here is the mean. And the ultimate tensile strength is 500. And the endurance limit is 200. So the design equation is looking like this. Yep. Okay. So this is yield line. This is Goodman. This is Soderberg. Okay. So my design point is 1 4 something. So here is 1 4 something is right here, and 30 something. So design point is here. So if you study the distance, these normal distance would be representing the safety level. And from here, still it's a hand drawing. So from here, the distance from the design point to the Soderberg model is the shortest. So it's the most conservative model. And the one to yield line, so this one is shorter than the one to Goodman. So my drawing is kind of right, but not exactly accurate. But still, you can I observe the one to Goodman could be the longest. So what does it mean by longest? That means in this concept, you think you have a greater safe margin. So you are taking more risk. You are willing to take more risk. But if you have a shorter gap, that means you think you are closer to failure. You want to be safe. You are conservative. You will play conservatively. Okay, so that's how the distance mean, and that's how this distance represent in numbers. Okay, and if we compare to what we did earlier in the previous lecture, without consideration of stress concentration, we end up with different numbers, and they are all larger than what we have today. So without stress concentration, we think we are safer. Right? Because if we don't consider stress concentration, the stress analysis, the stress values would be lower. So of course, we will think we are safer. And the calculation tells the same thing. The calculations tells us our safety level are higher. Okay? So that's problem 1. Do we have a problem 2? Yes. So if you understand what happened in problem 1, now let's take a look at problem 2. There is only one thing that is different, which is this time the shaft is rotating. If you rotate the shaft, then something is different. What is different? Okay. This is the exact same moment analysis, but since the worst loading position is right here, right? And earlier we said, okay, this point is having this tensile stress, but as this point moves to the bottom, right here, it's being compressed with the same level. So without fluctuation, that particular point will be experiencing some kind of stress variation along time, like this, positive, negative, positive, negative, because the shaft is rotating. However, because of the fluctuation of the bending moment, so the stress level goes up and down. So you can kind of think the fluctuation of that uh, of the moment of that particular point looks like that. So it's really going up and down, but sometimes is up and down in the positive area, sometimes is up and down in the negative area. So this is another example about frequency. How do you know what's the frequency of the rotation or what's the frequency of the belt variation? The problem didn't mention it. So what do we handle this kind of problem? We just study for the most extreme case. Because if the design survives for the most extreme case, then we're fine. So what's the most extreme case? The most extreme case is like at some point, that particular point will be moved to the bottom, and sometimes when the point is at the bottom, it's experiencing the largest bending moment. So sometimes the stress, the moment goes to the most possible, most negative value. And for some other cases, it will be right at the top, the most possible, most positive values. So with these two extremes, you can see that the mean of stress is zero. Mean of the moment is zero. If you choose those two as your extreme conditions, so the mean is zero and the amplitude is this large. The amplitude is 271724 right there. So because of how the shaft is rotating, the fluctuation condition of bending moment is changing a lot for a particular point in the shaft. Nothing changed for the torsion. How come is that? Because you are twisting the shaft, sometimes tighter, sometimes loosen a little bit and tighter again. And your design point is rotating around the same axis, and then no matter which angle your design point is, it's always experiencing same kind of fluctuating twist. So no matter where the point is, the fluctuation level of the torque is the same. So for the fluctuating torsion is the same way of studying based on this problem. Okay. So once you have those two statistical analysis on bending moment and the torsion, then just everything is the same for the rest. It's just the different numbers. So do the same thing, plug in numbers. But what will be interesting is that since the after how you plug in the values, you realize the first principal stress become 4.6 megapascal, but the amplitude is 161. So it's like a 4 plus and minus 161. So sometimes it flips to the compression part. So this point is like a 4.64 plus and minus 161.97. It's like this. So sometimes this point goes to here, sometimes this one goes to here. The first principal stress. Okay, the second principal stress remains somewhere here. It's like not varying too much. Okay, so what does it mean? It's like your Moore circle when it goes to this large, it's like a little Moore circle looks like this, and when this value goes to the bottom, it's like a Moore circle looks like this. So it's changing its shape in this way. Okay, so you can. It's like every moment at the middle. It's like something like this. Oh no, it's like a. And we go. Oh no, not in this curve. Sometimes so it's like this. Because sometimes it's small, right? So it's not this curve. Sometimes it's small. It's like this. Oh, it's like this. So the Moore circle becomes small, large, like this. So when the Moore circle are on the right hand side, it has a tensile normal stress. When it shrink to here and then become bigger on the left, it's compressed. Okay, so it's a quite unique result. But anyway, as long as we have numbers, we can solve it. So plug into the von Mises stress, and then we realize, plug into the von Mises stress, and then plug into the design equations. We found the safety factors are different. Okay, so these are the values without stress concentration, and again with stress concentration, they are lower. Yes, they are lower. And I would like to compare with the previous problem. Previous problem, we have 141220135. So 141220225. What was that? 135. Okay. So these are the values in the earlier problem. And I had a drawing. I shouldn't have erased it. It was like this and this, right? And this is the mean part. This is the amplitude part. Earlier, I said the design point would be somewhere here, but now we can take a look at this particular problem. Since the shaft is rotating now, the amplitude, the fluctuation is larger, but the mean value is smaller. So mean value is very small, and the fluctuation is up to here. So this is a design point when the shaft is not rotating. This is with rotation. And they all, in this particular point, there are also three different distances. And for this case, for the numbers that I chose, if it's rotating, the design point sort of getting closer to the safety limit. So in this particular case, the second one, we are having a lower safety value because we are having a closer distance to the good limit. Here is larger. Okay, but for some other cases, it doesn't matter too much. Not changing too much. So it really depends on the load condition, and also depends on the model you're using. So from here you can tell fatigue is quite sensitive to the low condition. Okay? So that means as a mechanical engineering designer, in the future, when we are designing for something, if you know about the theory, you know how to do estimations, you definitely have room to improve your design, to make your design stronger or lasting longer cycles. And if one day you are designing for something and you want your design to fail after a certain cycle, this is uh, this is the analysis you should do. Why would you want something to fail after a certain cycle? Because you want the customer to buy the new one, right? So you need to control the reliability properly, so you know after a certain cycle, only certain percent of the customer experience fail part. So the failure rate is not too high, so people don't complain about it. And so it's also about marketing and customers' behavior. It's very related to business, right? So this course is also related to business. If you know engineering and statistics. So before this lecture, we are geeks about forces, deformations, but we don't care about how the customer think about. But in this course, it's very related to that. Okay? So the next exam will be some problem like this, but it won't be this complex. I will try to make it a smaller one so you can solve it within 2 hours. Okay, it may be two separate problems, so I don't know. I haven't designed the problem yet. Okay, so it's next week, right? Okay, so if you have, so I recommend you go back and do some practice and think about various kind of scenarios so you know how to study the fluctuation of forces, and then you won't make a mistake on choosing the mean value and the amplitude value. Usually that's where you make a mistake. Because if you think about the fluctuation condition wrong, then whatever you do afterward will be incorrect. Okay? So please practice it. Okay? Thank you. Bye-bye. Oh, if you haven't haven't do the roll call, it's here.